Hello everyone. So we are now almost at the end of the course. In the previous lecture, we already have seen some of the sensor circuits. We started with simple basic circuits associated with sensors, for example, say voltage divider. And then we also have seen another very basic circuit which is Wheatstone bridge. And we have discussed how these circuits will help us in interfacing a sensor with the system. So in case of voltage divider, you can remove one of the resistors and can put a sensor in that place if your sensor is resistive, of course. And then in fact in other sensors also you can take advantage of the voltage divider circuit. I'm just giving you a example. And then you can get the analog voltage output from that divider circuit and can take it forward to the next level of this next level of your system. Then we have seen what are different amplifiers. So there are multiple amplifiers, and then you can also use those amplifiers for various purposes. We also have seen instrumentation amplifier, which is again a very specific kind of an amplifier which helps in making the sensor system. Today again in this lecture we will see those basic circuits, and I will show you some of the basic experiments so that you can understand how these basic circuits can help us in developing the interfacing circuit, or how these circuits can help us in integrating sensors with a relevant system. So let us again see the first basic circuit that we have discussed previously. It's voltage divider. In this circuit you have two resistors R1 and R2. You apply voltage V1, say voltage V1, that is the applied voltage, across R1 and R2, and then you can take an output from here which will be a function of say R2 and R1 both. So basically the input voltage, that is V1 in this case, will be divided between R1 and R2 based on their resistance values. So in this case V2, the voltage V2 is equal to R2 divided by R1 plus R2 into V1. That we have seen, and we also have derived how it came. So basically this is a ground, you may consider this as ground, and then your V1 is equal to R1 plus R2 into V1. So V1 meaning in this case you can consider this as V in, say input voltage. So it's like V2 is equal to R2 divided by R1 plus R2 into V in. Similarly V1, that is the voltage drop say across R1, is equal to R1 divided by R1 plus R2 into V in. So this is how you can measure or calculate the voltage across the resistors. Now one can also replace this resistor with a resistive sensor, and then you can take this potential as the sensor output and then can connect this with the rest of the systems. So to give you an idea, a simple experiment is shown here. So this is your breadboard, and say you are connecting resistors in the breadboard in series, the way it is connected in the voltage divider circuit. So the circuit is something like you have one resistor R1 and another one in series, say R2, and then you'll take output from here. So this is your second resistor, you are connecting in series. So you have one resistor already connected, now you are connecting the second one. Okay, so you can see that both the resistors are now connected in series. So once you have two resistors connected in series, then the total resistance is RT is equal to R1 plus R2. Now we are connecting the voltage source. So this is a 9-volt battery. So we are connecting across both the resistors. So it's a 9-volt, for example. Okay. So in this case, we are connecting the battery across this network. So once you have the battery connected with both the resistors, what we are doing is we are taking one output from this point. Okay. And at the same time, currently we are connecting one wire here and one wire here. So this is like, this is connected in here. So you have now two wire, 1 and 2. Both these wires will be now connected with a multimeter. So now we are connecting the wires with two probes of a multimeter. These are the crocodile clips, and we are connecting the circuit with power source and with multimeter. This is your power source, this is your multimeter. So this is the multimeter display. Now, just after connecting both the wires with multimeters, you can see that 7.23 is the voltage across R2. Say this is across this resistor, right? Total voltage is 9 volt. Now that voltage is divided between these two resistors. Now the voltage across R2, I mean this resistor, is 7.2 volt. Now we are replacing this resistor with some other resistor, just to give you an idea that when you change the resistor, the voltage should also change. Let's see, when we change this resistor, this is another resistor, and now we will connect this resistor with the previous resistor. So we are just replacing the resistor. So you have now a different resistance value. Now once you connect the resistor and then the moment you switch on the multimeter, now it is giving 8.06. So once you change this resistor, the voltage across R2 will also change. Although your total voltage, that is the applied voltage, is 9 volt in both the cases. Now what we will do is we will replace this resistor with a thermistor, that is a temperature sensor, which is nothing but a resistor only. So we are connecting this thermistor in place of our second resistor. So we are removing the resistor and now connecting this resistor in the circuit. Now once it is connected, the voltage now is 2.36. So this is the voltage across the temperature sensor here. So you have replaced this with, say, RS. RS is the temperature sensor value. Now this voltage you can calculate based on the equation that we have calculated. V2 is equal to R2 divided by R1 plus R2 into Vin. So you can calculate using this equation. Now see, when you touch the sensor, the voltage value is changing because now the resistance of this sensor is changing. Now if the resistance R2 changes, then your V2 also should change. That is what you can see over here. The moment you take it out, then the resistance value will go in the previous value. Now we are applying, say, hot air, using an hot air gun. We are applying hot air. Now because the temperature around this sensor is changing, so you will find the same change over here in terms of voltage. Now you can take this, that is this analog output, to the next level of the system. So you can use that output for your sensor system design. So in this experiment, you can see that if you replace this resistor with a sensor, then you can also integrate the sensor in a voltage divider circuit, and you can take the analog output to the next level of the system. Similarly, we also have seen Wheatstone Bridge, and Wheatstone Bridge has 4 different resistors: R1, R2, R3 and R4. Now, if your Wheatstone Bridge is balanced, that is, if R1 divided by R2 is equal to R3 divided by R4, then VAB, that is the potential here, will be equal to 0. If there is any mismatch, then you will find certain potential in the VAB terminal. Now, in this case, again, just by applying the voltage divider rule, you can calculate VA and VB value, and then you can figure out what is VAB, that is VA minus VB. Put those values over here, then you will get the expression. Now, this circuit also can be used for sensor system design, where you can now replace 2 resistors with 2 sensors, and in this case, one sensor can act as a reference and other can act as a measuring device, or the combination of both will help to reduce the environmental effect. If there is any ambient change or change in the ambient condition, then this can be neglected using this type of arrangements. Now, again, let us see with a small experiment how the Wheatstone Bridge can help us in developing a sensor interfacing circuit. In this case, we are taking 2 similar resistances, as you can see over here, and we will connect the same in the Wheatstone Bridge structure. Okay. And we will see what is the response. So here you have R1 and R2. Now we are connecting R1 and R2, and then we will take 2 other resistors, R3 and R4 as well. So the resistors in this case are similar. So this is the new set of resistors that we are connecting in place of R3 and R4. Our purpose in this case is to maintain R1 by R2 is equal to R3 by R4, so that we can get a balanced Wheatstone Bridge circuit, and then we will try to check if that balanced Wheatstone Bridge circuit can provide us VAB is equal to 0 or not. So here we have now 4 different resistors connected in a Wheatstone Bridge circuit. So now 4 resistors are connected the way it is shown over here, R1, R2, R3, R4. Now we are connecting 9 volt voltage source. So this is a 9 volt battery, you can see over here, and we are connecting this 9 volt battery the way it is shown in this circuit. And at the same time, we are connecting a multimeter to measure the voltage, VAB voltage. So once we connected the multimeter, we can see that because R1 by R2, R3 by R4, these ratios are balanced the way we have seen, the potential VAB is equal to 0. You can see in the multimeter reading. So the potential is 0 because your R1 by R2 is equal to R3 by R4. Okay. Now what we will do is we will make this entire Wheatstone Bridge circuit unbalanced. We have taken another resistor, and now we are replacing one of those resistors, one of those used resistors, with a new resistance value or new resistor, so that R1 by R2 is not equal to R3 by R4. We are purposefully making this entire Wheatstone bridge unbalanced. So the moment you make this circuit unbalanced, you will be able to see that there is a, so in this case the moment you make this circuit unbalanced, you can see there is a voltage VAB. So in this case the Wheatstone bridge circuit is not balanced. So you can see that there is a value of VAB, right? It's 1.6 or so. This is VA, this is VB. Now we are replacing these two resistances with identical sensors. So we have taken two thermistors and we are replacing R3 and R4 with similar thermistors, and both the thermistor has same resistance value. So in this case R1 and R2 is same resistance, R3 and R4 is same resistance. So your R1 by R2 is equal to R3 by R4. So it's basically 1. If R1 is equal to R2, then this is 1:1. R3 by R4 is also 1:1. That is how we are creating a balanced Wheatstone bridge, so that we have a output VAB which is equal to 0. Now see, in this case you have a very slow voltage in the multimeter reading because it's more or less balanced. The moment we put hot air using this hot air gun, you can see that you will figure out there are certain voltages in the multimeter because of this VA and VB values. So in this case, because you are applying, but in this case also the applied the voltage that you can see in the multimeter is not very high. The voltage in the multimeter is not very high because when you apply hot air, this will change the resistance of both the resistors. So the relation R1 by R2 will be almost equal to R3 by R4. If you change the ambient condition using this hot air gun, you are changing the ambient condition around this sensor system. Now the ambient condition is different for both the sensors, and hence the Wheatstone bridge is still balanced. That's why you don't see a big VAB potential, although there is a very small potential because you are applying the hot air gun from this side. So there will be some sort of temperature mismatch maybe, which may lead to a very small voltage, but this is not significant. That's why if you use two sensors in a Wheatstone bridge circuit, you can get rid of the environmental effect. But if you use only single sensor, as we have seen in case of voltage divider circuit, if you use only single sensor and if the temperature around this sensor system changes due to any reason, that will affect your reading or measurement. For example, say in this case the entire sensor system is designed to measure say body temperature. Now this sensor should measure the body temperature if you bring that sensor in touch with your body. But if the ambient temperature is also changing or if it's different, then you will get a wrong result. But if it's in Wheatstone bridge structure, even the ambient temperature is changing, you are using this hot air gun to change the ambient temperature, you will see that the effect of ambient temperature is very less in the entire sensor system. In individual sensor, there is a significant effect, but in case of Wheatstone bridge structure, the effect is minimum, very less. Okay, that is an advantage of using Wheatstone bridge. So in this experiment, we have seen how Wheatstone bridge can help us to reduce the ambient effect, Okay, this is one of the advantages that you may get from Wheatstone bridge structure. So as far as the sensor system is concerned, we have discussed the basic interfacing circuits that we use usually here. We have discussed filters, what are the different filters that you may use, active filters, passive filters, and briefly have mentioned what is Butterworth filter, what is Chebyshev filter, although I haven't discussed these filters in details, but at least after this course you will be able to understand what is a filter and how filters can help us. Then we have seen various amplifiers. Amplifier is a very important component again. In order to amplify the signal, if your sensor output is less, then you need to amplify the signal for processing. We have seen different amplifiers, and the signal conditioning part to some extent is covered. Thereafter, you send that signal to ADC, that is analog to digital converter. Then you send the signal to microprocessor. Say you use Arduino boards. So Arduino board has an ADC as well as a microcontroller, Atmega microcontroller. For example, if you take Arduino Uno, then it has an Atmega microcontroller, and then you connect that processor with a memory or a display so that you can see the reading. This part is again very important. However, in this course, this discussion is not added, but the analog front end or the very important part, which is a signal conditioning part, is to some extent covered. Okay, and then you can connect this with an ADC, with a microprocessor, and with a display, so that you get an entire sensor system out of the say sensor or out of your desired application. So we are almost at the end of this course. In this course, if I summarize, we have covered different sensors, including different types of sensors. For example, if it is a thermal sensor, how a temperature sensor works, how a thermal sensor works, and then how capacitive sensors work, or how can we design a capacitive sensor. We have also covered various other types of sensors, including say acoustic sensor and microfluidic sensor. So the idea of this course was to provide you the basic information associated with different sensors and sensor physics, and I hope to some extent we have covered most of the types of sensors, although there are a lot of other sensors present, but in a single course it's very difficult to cover all types of sensors, but the one that we covered will be really helpful, I hope, for you to decide which type of sensor you should use for what application. Sensor is a very interdisciplinary field, so one should know different aspect of sensor, right from chemistry, physics, engineering, biology. If you are developing biosensors, so you also should know some sort of biology. So it's a very vast field. It's very difficult to cover all the aspects, but the target in this course was to give you the basic idea about sensor physics and different types of sensors, which probably you have learned. Then we have also seen different fabrication and characterization methods, as I have mentioned over here. So what are the different fabrication methods, what are the different characterization methods, that also we have seen, right from basic microfabrication technique to micro nanomaterial characterization techniques. For example, electron microscopy, optical microscopy, so on and so forth. So this fabrication idea will provide you basic understanding regarding different sensor fabrication methods. However, it's not limited to microfabrication techniques or the techniques that I have discussed in this course. There are various other techniques. So various other techniques available. There are many non-conventional techniques as well, which people generally use for developing different sensors. As for example, say if you want to develop a flexible sensor or flexible electronic device, in that case the fabrication technique may be very different than a conventional, say, MOSFET based sensor. However, in this course we tried to learn many other fabrication methods, characterization methods, and finally we touched upon sensor system and sensor circuits, the basic sensor circuits and the basic signal conditioning circuits. And then also I've seen that the entire sensor circuit also has several other components, so that you get a comprehensive idea about how a sensor system or the basic building block of a sensor system looks like. With this, I would like to conclude this course. I hope that you have enjoyed this course, and after this course you will be able to design or develop different sensors and sensor systems. I would like to offer similar courses in future as well, so that you get a comprehensive idea about various other parts of the sensors. This is a basic course to provide most of the details associated with sensor technologies. I tried to cover the entire spectrum of sensor technologies, so that after this course you know what are the different components as far as the sensor technology is concerned. I would request you to self-study or to do some self-study in this area, to read some books, some literature, some research papers, and I hope these research papers or the reference books will help you to gather more knowledge in this field. Thank you again for joining this course. Hopefully we'll meet in a different course in future. Thank you very much.